Hi Year 12. This lesson we are going to turn in our books to page 135 and we are going to consider reaction profile diagrams. Now earlier on in the year when we studied chemical reactions, we said that chemical reactions can only happen when particles collide or crash into each other. Now if the reaction is going to happen, if the collision is going to be successful, the particles need to collide in a certain way, but they also need to collide with a minimum amount of energy, and this minimum amount of energy is called the activation energy. Now the first thing we're going to do is remind ourselves of that definition. So we're going to write in then on page 135 that the activation energy is the minimum amount of energy required for a reaction to happen. Now if we look at the energy profile diagram that we've got on the screen just now, you can see that we have got energy on the y-axis and we have got progressive reaction then on the x-axis. Now if we look at the energy that the reactants have, they have this amount of energy. But when these reactant particles are colliding, they actually take in energy to break all the bonds. They rearrange themselves then when all the bonds are broken. The atoms rearrange, they form new bonds and they form the products. Now in this example, the products actually have less energy than the reactants. But what we're really looking at is this activation energy. So you can see that this is the energy taken in to break all the bonds, to allow the atoms to rearrange themselves so that they can go on and form new products. And it's an important definition to remember. Now we're going to draw some of these reaction profile diagrams, but write in then that a reaction profile for a chemical reaction shows how the energy of the chemicals change as the reaction proceeds. And you can pause the video, remember, as you need to. Now, like I've just shown you then, a reaction profile is drawn as a graph sketch of energy on the vertical axis against the progress of the reaction from reactants to products on the horizontal axis. Now, there are two types of reaction profile diagram that we will need to draw. We need to draw one to show an exothermic reaction, and we need to draw one to show an endothermic reaction. Now we're going to start with the exothermic reaction. Now I want you to draw the axes first and make sure that you have labelled the axes because there will be marks for this in the exam. So on the y-axis, we have chemical potential energy, or just energy is enough. And on the x-axis, we have the reaction progress, or sometimes you'll see it as time, but either is okay. Now we've got to be very careful because this is showing an exothermic reaction that we have the energy level of the reactants and products in the correct place. And then the important thing is that the energy level of the reactants is higher in this example than the energy level of the products. Now take care that you label each part of this diagram. So like before, the reactants, whatever they may be, have got this amount of energy. They take in energy over the course of the reaction then to break the bonds when the particles collide. The atoms then in the reactants rearrange themselves and they give out energy as they form new bonds in the product. Now we've already mentioned the activation energy. You can add that into your diagram, but we're going to add in this label in red that's really important. Now this is the heat energy. This represents the heat energy released by the exothermic reaction. Now delta H is just a short way of writing the amount of energy. Now we said in our last lesson that exothermic reactions have negative energy change values, and this reaction profile is really showing this. So if you look at it carefully, you can see that the products have less energy than the reactants, so therefore heat energy has to be given out, hence it's an exothermic reaction. The arrow's pointing down, so this delta H if we were to take away the energy of the reactants away from the energy of the products, because the reactants will be a higher number and the products a lower number, this will have a negative value. And this is really important because it's an exothermic reaction. Now, I could explain it just here in the little red box if I think about the amount of energy. More energy is released when these bonds are formed, and we will talk about that more in another lesson, than is absorbed during bond breaking. So overall, energy is released by this exothermic chemical reaction. So pause the video as you need to, draw in the diagram in the space, and make sure that you have it all labelled. Now, just below the diagram, a good explanation then. So in an exothermic reaction, chemical energy in the reactants is converted into heat energy, which is released. This means the products have a lower energy than the reactants. The change in energy, like we've just said, is written as a negative number. Now we're going to go on and we're going to consider an endothermic reaction. Now remember, endothermic reactions take in heat. So like before, start with your axes, label up carefully the y-axis and the x-axis, and be very careful with the level of energy of your reactants and products. This time the reactants have a lower energy level than the products. Now if we think about that, like before I have said that in a chemical reaction, the particles or the reactants collide, they take in energy to break all the bonds, the atoms rearrange themselves into the products, and they give out energy then as they form new products, as the new bonds are formed. So if I were to sum that up, I could say that more energy is absorbed by bond breaking than is released during bond forming. So overall, the energy is absorbed by an endothermic chemical reaction. Now, we need to add in this blue arrow. Heat energy is absorbed, like we've just said, by this endothermic reaction. If I look at the energy value of the products and the reactants, well, the products have a higher energy than the reactants do. So if we're taking the energy of the reactants away from the products, this change in heat energy will be a positive number. And we said in the lesson before this that all endothermic reactions have a positive energy change value. So the fact that this delta H, this energy change, is positive is really important. So pause the video as you need to, draw in the diagram at the top of page 136 and make sure that you have it all labelled. Now we're going to write in a good explanation. In an endothermic reaction, heat energy from the surroundings is converted into chemical energy in the products. The products have a higher energy than the reactants. The change in energy is written as a positive number. Now, our last of the lesson today, then, we need to consider catalysts in these chemical reactions. Now, we know from our rates of reaction studies earlier on that a catalyst speeds up a chemical reaction. The catalyst itself is not used up, but we're adding a little bit to our knowledge just now, and we are adding the fact that a catalyst speeds up a chemical reaction because it provides an alternative reaction pathway with a lower activation energy. So these reactants can get away with reacting and colliding with a lower amount of energy. Now, if we show this in an energy profile diagram, again here I've got the energy of the reactants and I've got the energy of the products. Now, this is an example, remember, of an exothermic energy profile diagram. But we're not really concerned with that just now. We're thinking about this activation energy. Now, if you look at the green arrow is the activation energy without a catalyst, whatever that number would be. The red arrow then, if we look at the red pathway, The red arrow then is showing us the activation energy when we add that catalyst. So the blue pathway is the reaction without the catalyst. The green arrow shows the amount of energy that's needed. The red pathway then is the activation energy with the catalyst. That's the alternative pathway, and we can clearly see then that the red arrow is a smaller number. The activation energy in this alternative pathway is lower, and it explains really why this catalyst is able to speed up the chemical reaction.